Years ago, when I joined the IBL, spike sorting was a black box, and they used to us, and they told us, okay, run this on the data, and this is what we did, and what I'm going to show is all of the lessons that we've learned over running this pipeline over and over again, and that culminated in a rerun of all of our data that finished actually this weekend. So in this talk, I'm going to show you a lot of data. And if there is one thing that you should take away from this presentation is that you should look at your data. It's a really good habit to have. And there is no way around it. Spike sorting is a very complex process. It's not a single process. It's plenty of different ones. And you have to look at it at every step if you want to understand what's really going on. So before I go into the depth of spike sorting, I'm going to set the problem, just presenting the IBL. So the IBL is a consortium of 22 labs in 6 countries, 12 experimental labs that are going to reproduce the same experiment in 11 locations. We are centralizing all of our data in San Diego here on this presentation. This represents 70 researchers full-time. And 10 full-time staff. I'm going to present very quickly the task. The reason I'm mentioning the task is because you need to know that it's mice. It's a head-fixed mice, and there is a reward. The mouse is making a decision according to a stimulus that appears on the screen. If the mouse makes the right decision by turning the wheel to put the stimulus in the middle of the screen, the mouse gets a reward. Otherwise, it gets an error tone. So this experiment is reproduced thousands of times across 10 different labs, and we get the data to spike sort it. So it represents, in this case, the flagship project is what we call the brain-wide map, where we recorded this experiment in several labs, and that gives you an idea of the span of the recording. So there are two challenges here. One challenge is only the size of the recordings, the sheer number of data. The data size is huge in itself, which means that a rerun or a run itself is a complicated process. The second issue is the variability of the data. When you record from all across the brain, you get very different signals. I'm going to illustrate this with some raw data displays. The first one, so you have to get used to those displays because we're going to see a lot of those today. This is a voltage map of an electrophysiological recording. Here we are looking at something like 50 milliseconds. The time is in the abscissa, and this is a 384 Neuropixel 1 channels in this direction. Here the columns show the Allen brain regions color code. So here we see we are in the hindbrain. In the middle, this is the cerebellum. And in the right, we are in the visual cortex on top, the hippocampus, and then the thalamus. And what you can see that all of those regions show very different characteristics on the raw data and on their electrophysiological signature. What needs to be understood as well is that most of the spike sorter we are using have been fine-tuned to work on the upper right part of this displays, while the middle part, the cerebellum and the midbrains, are much more difficult to spike sort. So this being said, we're going to dive into the spike sorting at IBL, and I'm going to show a bit the algorithm changes we had to implement over the years on top of PyKiloSort. And I'm going to go through modules here to pre-processing, drift registration, and post-processing. And you've seen some of those methods presented before already. Then I'm going to go through standard quality control outputs and why looking at the data is so important, and why we can do better in Spike interface or in other processing software that output those quality controls for users to look at. And the last thing I wanted to mention today is about the rerunning at scale. So we just finished rerunning 700 insertions, and I want to talk about the implications of doing this because it's a bit different than doing the spike sorting after an actual acquisition. So the spike sorting modules, as has been presented before, the spike sorting is a continuum of processes that are plugged in together. So here I split them in 4. The first is the pre-processing. Second part is the drift registration, where we try to correct for the motion of the probe. The next part is the clustering, where we do the classification of the waveforms. And the last part is the unit curation of our post-processing. All of the items that I'm mentioning here, I'm going to go through them, are the changes relative to the pi-kilo-sort standard algorithm that have been implemented in our fork and partially in Spike interface. The bold items are the items that have been changed in the rerun we did recently. And those are the items that triggered our decision to make a rerun on such an expensive rerun. So I will start with the pre-processing, and I will start with the rephasing of the channels. So at the very beginning of the ABL, we had data like on the left. And once we applied the pre-processing of the original spike sorter, we ended up with the data on the right. And as you can see, here we have a large stripe, which can be removed, but we had a lot of noise after applying the common noise rejection. And this was due to the fact that all nodes of the electrodes are sampled synchronously, and we had to correct for that. We didn't know this, so we created an algorithm to interpolate the channels, as you can see here in C. And then the common mode rejection works much better, as you can see in D. So that was the first lesson learned, we really need to apply this. And it's also the same for the LFP. So it's an important step. In terms of implementation, we implemented this in the frequency domain so that we didn't have to do time domain interpolation. Another thing we had to do is the channel rejection. So what we had to do is to do an automatic way to detect the bad channels. So here what I'm showing on the C is the original probe recording. And you can see that we have two kinds of bad channels here. In blue, it's what we call the dead channels that are in the middle. And in red, this is what we call the noisy channels. So we have to compute a set of automated features, as you can see on the left, that would allow us to detect what could be those bad channels. And then we have a choice either to remove them or to interpolate them. As you can see on the right, we chose to interpolate the bad channels so as to have a consistent probe layout for all of our spike sorting runs. This was quite important for the outcome of the pre-processing, as you can see here. So we have another kind of bad channels here on the top that are channels outside of the brain. And the problem, it creates a huge discontinuity as even the striping noise that we get across all of the channels is not recorded outside of the brain. So when you apply common mode rejection, here we have an edge effect that was leaking into the parts of our electrodes that were recording in the brain. And as you can see, if you do proper channel detection and interpolation and removal before applying the pre-processing, you end up with a better signal. So what can possibly go wrong when you do this kind of channel detection? Sometimes you don't detect that the channels are outside of the brain, and this is what you get. So this is raw data with the overlay of the output of the spike sorter. Each dot is a spike detected. The red dots are the spikes that are in units that are not passing quality control. The green dots are passing quality controls. And here, as you can see, the channel detection failed, and we get a lot of spikes that are outside of the brain. Wow. So that's the next part I wanted to discuss is the spatial filter. So once we apply the channel detection, we interpolate the channel, then we want to do the common mode rejection, so common average referencing. At IBL, we chose to do a spatial filter instead. So it's kind of you can imagine the common average referencing as removing the DC component of the probe across the spatial direction. But you could imagine applying a filter that will capture a bit more. The reason of applying a spatial filter is this example. So here on the left, you can see the raw data for which you have striping, but the striping does not span the whole probe. So when you do the median subtraction in the middle, you end up with adding noise on the top because you remove the average. So here the idea is to apply a spatial filter is in order to take care of those artifacts as well so that we can go into whitening with a cleaner signal. Another example I'm going to show is here in cerebellum. So you can see it looks like very noisy data, but actually it's not that big of a deal. As soon as you apply the proper pre-processing, you get a nice cleanup of the data. So there are drawbacks in applying a spatial filter. So there is a discussion going on here because the drawbacks of this is first, it's expensive to compute. Now, the second thing that could be problematic is that it's not suitable for all of the applications. So here on the left, I can see this is the raw data that is not very striped. On the right, this is this striping applied. We have this kind of what we call butterfly effect. You can see that this spike is very high amplitude. The fact of applying a spatial filter, a common average, is going to add noise on the sides, which means that it's not a problem for us because if we go into whitening, this is going to be collapsed by the whitening. But if your application is to extract waveforms for analysis or for classification of units, this is probably not a pre-processing you want to do. Yes, in this case. Yeah, I don't think this makes a lot of difference, but we could try. Yeah. But yes, maybe we can improve this method. But I'm just saying that here, really the idea I would like to bring across is that maybe not all of the processings are suitable to all applications. Maybe one processing is good for an application and another one is good for another. Another issue we started to see is that I'm going to show a raster plot here. This is the time. This is one of those drift plots zoomed in. And we can see some task-related events here in green. And at the task-related events, those are the rewards. And just after the reward, what you can see, you have stripes of activity that show up across the whole probe. This is very unlike an event that we should detect normally on a neural data. And indeed, this is due to the saturation of the probe. In this case, this is saturation that is due to the fast voltage change when the mouse is leaking the spouts. Here, the probe is not really saturating in the sense that the maximum gain is not exceeded. It's just the derivative of the voltage is going up so fast that it creates this artifact. The problem with the saturation is that the spike sorter is going to pick up on those. This is not too much of an issue because if we can detect saturation, we can just remove the spikes, right? The problem we have is that the hypothesis is that this is going to throw off the clustering. The fact that you include so many bad waveforms, it's going to go into good clusters, and the clustering or the quality control is not going to work as intended on those. And this is indeed what we saw after detecting the saturated events, muting the saturated events before doing the whitening phase, as here. You can see that all of a sudden, with exactly the same parameters, you get more detections. You see some spikes that get detected all of a sudden because of the whitening process that is more stable once you deal with the saturation. So that's one thing to do, is to deal with the saturation, both when the voltage is exceeded and when the derivative of the voltage exceeds the threshold. Another thing, so this is the result on the raster before and after. So data that was really hard to analyze, especially in this case, it's a big problem for scientific analysis. If you have something that is reward dependent, an artifact that is dependent to something on the task, it's really a problem for analysis. In this case, we were able to take that out. Another thing I wanted to mention is the whitening process. The whitening is something that it's called zero component analysis. If you know what is PCA, it's basically a PCA without the rotation components. In practice, what happens is that at several parts of the recording, 50 parts, we're going to extract a small matrix, voltage trace, and we're going to compute the covariance matrix and compute the inverse, the eigenvalue decomposition of this covariance matrix. And we started looking at the condition number of this matrix to see how invertible it is and how nice the eigenvalue decomposition can be. And what we started seeing is that if I show the condition number as a function of the diagonal energy over total energy of this matrix, that we have big outliers. So the condition number should be confined to this region here, but all of those things are probably noisy recordings, and those are very noisy recordings. So we started dig a bit deeper in this, because this is really deep into the spike sorter. So we say, okay, let's have a look at the data. Let's have a look at what it changes. So this is an example of such a condition number around 40, 50. And this is the raw data. This is the described data. And this is the whitened data when you apply this whitening matrix. And what we saw that this whitening matrix was kind of noisy. So we added some stabilization based on the bad channel labels. So we added specific weights there to handle those. And the outcome of this is to first remove the bad channels that are on top here. But also, as you can see on this part, we see a lot more activity that was muted because of the whitening in this part. And this is really tricky with the whitening is that the fact the whitening matrix could be non-local sometimes, noise in the data are going to leak in one part of the recording, one depth of the probe is going to have an impact at another depth. And another problem with this that is not solved as of now is that if you record cortex with thalamus at the bottom, or if something else at the bottom, you will have a different answer in the cortex, a different normalization in the cortex because you had thalamus recorded with the cortex. And this is a problem we'll probably have to solve in our algorithm. So I went through the pre-processing part. This is what we did much of the work. Actually, we completely removed the original pre-processing and swapped it out. The second part is the drift registration. We swapped the drift registration in the rerun, and I'm going to show some results exactly from the method that Charlie showed earlier. So I need to explain a bit what's going on here. There is so on the left, we have the spike detection done by Dart, the Dart program, the dredge program that Charlie shown. This is for the full recording. This is the drift map. Okay. On the right, this is the same drift map for the same recording as a function from kilosort 2.5. In kilosort 2.5, you have a drift detection, a spike detection that is done only once, a throwaway detection just for the purpose of computing the drift. On the top, we see the curves. The curves are the stability, so the higher, the better. And we have three curves. In blue, this is the dredge stability with the dredge spike. In green, this is the dredge stability with the kilosort spikes. And in red, this is the kilosort stability with the kilosort spikes. So in half of the recordings, we could see that dredge was doing substantially better than kilosort, regardless of the spikes detection. When we started seeing a bit of weird stuff where the green and the blue curve would be a bit different here, and you can see very weird events here. In some recordings that led to catastrophic collapse of the detections. So here on the left, you have a proper detection of the Dart raster, and in kilosort, catastrophic detection of spikes. This was this throwaway detection that is deep into the spike sorting, had a bug in the CUDA kernel. And if the spike rate was too high, it was throwing away part of the detection in the probe. And then the drift estimation was really bad. So here, the way you can see this is that the dredge with the kilosort spike, the green curve is really bad compared to the blue one. An example of that is more subtle and that is more across the lines of what we have in our data. It was a very extreme example before, is this, where at the beginning of the recording, everything is fine, and then you start seeing a mismatch. And the mismatch is due to those spikes that were not detected. And this was deep inside the spike sorter. So we have to put breakpoints, and we had to put outputs of this to say, okay, what's going on here? We had no feedback on this. So the next part I'm going to talk about is the clustering part. So here we found, it's actually Gael in this room that was looking at a lot of data, and at some point we start seeing that at a specific time, for all of the recording, we didn't have spikes detection. So here you can see the overlay of the spikes over the raw data, and no detection at all. And it was for all of the recordings. So I took the spike trains, and I did compute the derivative. I did compute the occurrence of those spike holes, and I divided this occurrence by the batch size of kilosort. and I got a curve like this. Here is the time in the units in the kilosort batch, the integer. And here is the number of occurrences of gaps in the spike train at those intervals. So we could see that actually we had this alignment problem in the windowing in the clustering. This was in the CUDA kernel, so we since fixed the bug in our PyKilosort branch. Another thing we looked at a bit earlier, according to the clustering, is the meta parameters. So a meta parameter is the spike detection level. So when we do the clustering, we need to do the spike detection, and we need to provide a level in standardized units at which we detect the spikes. And this is an example of cerebellar recording that are known to be tough. And this is the original spike sorting, where we have 660 units, over which only 50 pass our quality control. That's 8% of good quality of good units. And what we realized that by lowering the threshold, we have much more units, much more spikes, but we would actually increase the yield of a good cluster or passing quality control. So it means that in this case, there was a given threshold at which we were detecting enough spike to build enough support for the clustering to spike sort a bit better. And so for this, we realized that for at least for those regions, it will be beneficial to lower this meta parameter of the spike detection threshold. So that was for the changes done in the clustering part. The last thing I'm going to talk about is the unit curation. And I'm going to discuss a bit about how we compute this automated QC on the units. So once we have the output of PyKilosort, we compute three metrics: the amplitude of the unit, what we call the refractory period, the sliding refractory period, which is a fancy way to compute the refractory period without having to set a refractory period duration, so to allow to variable refractory periods. And the noise cutoff. The noise cutoff is a metric on the distribution of the amplitude of the units, where we say if we're missing the low part of the unit, it's not complete, so it's going to yield incorrect results, and we want to remove those units. So this is a Venn diagram of all of the bad units, which is 80 to 85% of the units. And what we can see that most of the units are failing the refractory period and the noise cutoff. Actually, most of units are passing the amplitude criteria. So I have plotted the distributions here of, so on top, this is the count of good units for the full run of the brain-wide map with the thresholds superimposed on the distribution. So here you can see the distribution of the refractory period metric, of the noise cutoff, and of the amplitudes. And on the bottom, it's the cumulative, so that you can see the proportion here. The green is the proportion of passing units for each of the metrics. So I've been over all of the algorithm changes that we have in PyKilosort, and the problems that led us to look at those specific parts of the spike sorter, and that had us do modules for those and to fix those problems one at a time. The second thing I wanted to say is that it's useful to have modules, then to have a quality control per each module. I'm going to show what we've learned and what we need to output for each spike sorting run in order to be able to control the quality of a spike sorting run. So first, for the pre-processing, we want to have raw data metrics such as the RMS. We want the PSD. We want to output the saturated intervals, so we can compute this from the raw data before we remove the DC offset. Those data sets are going to be useful for people doing analysis of the saturated interval. For the whitening, we know that we want the whitening matrix. We want the covariance matrix plots. We want to output those plots for each of the spike sorting to have a look at how it looks. We want to see the diagonal of this whitening matrix and with its conditioning, so that if it flares up, we can go and have a look at what's going on with this recording. We want to output the channels that have been detected and why they are bad. If they are a dead channel, if they are a noisy channel, or if they are out of the brain channel. The next part is for the drift. Lesson learned, we need to output the drift maps on which we compute the drift, because we would have seen this much sooner if we had done this. And this is an example of the before and after drift correction with the dredge. We want to output the non-rigid drift estimate in an array with the time points and the depth points, so that if we want to reapply this or do the inverse correction, or if we want to use this for histology, this is available. For the output of the clustering, we want physical units. I think it's important to be able to compare across regions. So spike amplitudes peak to peak in physical units, and the waveforms. And the waveforms, we want partial preprocessing. For the waveforms, we want them aligned, and we want some of the preprocessing, but not all. We don't want the whitening, nor do we want the spatial filter. We want to have displays of those, and those are displays of the raster map with all of the good units, all of the units on top, and only the good units at the bottom with the drift, with the computed drift on the top. I think a good thing we need to do, and maybe this hackathon, is to get the raw data and to apply the subtraction of the spikes model to see what is left. So all of this is standardized and documented in ONE datasets, and I think it will be a nice way to port them to Spike interface to have a standard way to look at those QC and look at those data. And this has proven very useful for us. Another thing that we did, and this was mentioned a bit before, is that for our experimenters and even for people doing analysis, we've built a website where here we put the electrophysiology inside the task setup. And here you can look at PSTHs, links with the raw data, links to the video, so that you can see a bit more what was happening during this session, and you can try to look at artifacts and if anything is wrong with the data. So the last thing I wanna say that all of those changes culminating with enough difference on a rerun that on the spike sorting that we decided to make a rerun. So we decided to do 700 insertions to start with and up to 1,000 eventually. And there was a lot of lessons learned when we started doing this. First of all, why do we want to do this? Is because we have a much better yield. Here now we are going to switch for the brainwave map to 40,000 neurons up to 70, almost 80,000 neurons. This is something we see in all of the brain regions. As seen on the bottom, we get more units in orange for all of the brain regions with these new parameters, new preprocessing. What did we learn is that first of all, you will always have some failures when you run those jobs because you have out of memory failures, you have some batch size mismatches. So we fixed almost all of them for now. I still have, I think, something like 9 going on. Each time you will have to put a new algorithm, you will have some bugs, some memory. So it's normal. You have to be very careful about this and to factor this in. The cost for us was 6 to 8 hours a run. So that's around 5,000 GPU hours. And it translated to, at least for the runs we did on AWS, was $8 to $12 for one spike sorting run on AWS. I'm very curious to see what that next talk will be about, because that's a big thing for us. So the lesson learned on this is that our algorithm is not designed to run on HPC clusters. It's designed to run on gaming computers in experimental rooms. So what we need to think about those modules as what are the CPU and GPU modules. So first we see that our CPU, our preprocessing right now, it's only CPU. And we have only the registration and clustering that run on GPU. And the last part, the curation, runs on CPU as well. We spend a lot of time on the job 1 and job 3, and we have to reserve GPU resources to do this, which is really inefficient. And if we were to split the jobs and to split the thing in 3 jobs, job 1, job 2, job 3, we could assign these to resources and to the CPU and the GPU resources and get them done faster. Second thing is that in HPC right now, there is a boom in usage of GPU. Everybody wants to train their LLMs. And here, I'm not sure right now if we should really gear our algorithm towards GPU acceleration all of the time. For pre-processing, which is not that intensive in terms of computation, it's basically reading in data, FFT back, and writing data. We may run 2 or 3 times slower on a CPU, but we may have much more resources, many more resources available and cheaper. So for large reruns, there may be a trade-off here. The last thing I want to talk about is maximizing the utilization. So what we can see as well is that we do not maximize the utilization of the GPUs, and we don't know how to run with GPUs with a large amount of memory. And I'm going to give you the example here is that when you write an algorithm, you want to write it so that it's parallel, so that you can set the number of jobs. You want to say to the user how much memory it's going to use and to have a way to predict the memory usage, so that you can get the available memory on your machine and launch the appropriate number of jobs. This way, you are able to max out the GPU memory, and your HPC maintainers are happy. A quick example on code, how does it look like, is that you get your memory info directly in Torch. Then you know how much memory per job you need, and you can set the number of jobs as was well computed. I have to say that here, this is an example of Dart sort, and the algorithm is really well written for that, because you can set the number of jobs. So it was very easy for me to avoid running out of memory and to scale to AWS GPU and HPC GPU and my local server computer GPU. So that's my conclusions. So the conclusion is quality control outputs. You need to look at your data. There is no way around it. If you are spending hours doing the recordings, we should make it easy for you to look at the data, but it's really important. And at every step. So those are the modules. They need to be benchmarkable, those modules, but they need to be verifiable as well. The modularization is important because for us, the way we work is incremental, is that we divide the work. We work on each specific task specifically, and then we can put it back in the main algorithm. But trying to solve it all at once is too long, too hard. This allows as well adapting to new acquisition hardwares. This morning, I was hearing about new probes with different geometries, different noise levels, sampling rate of 20 kilohertz, which is not what we have. All of this, we need to be able to check the pre-processing to make sure it works, because I'm not sure it will work. The last thing is that there is some work to do to improve our modules for high performance computing. We are not ready for that. It's fine right now for experimenters if you run your spike sorting as it comes. If you want to re-spike sort a large amount of data, there is a lot of work. And the last thing is that there will be other reruns because the spike sorting is far from being solved. With this, I would like to, the future directions is really in high performance computing. As I say, split modules in several jobs. We have to do some algorithm improvements, and here it's really high hopes for Dart sort or others. Adaptive thresholds and meta parameters. This is really something to work in several brain regions and make sure we get the most out of each one. There are a lot of work done on the units curation in different labs, and here we would like to look at automatic unit curation. So all of this is to be done with the community. We don't want to take this all of it ourselves. Happy to reuse what's being out there. And the last thing is benchmarks. Right now, I'm sorry, but it's a good start, Pierre, but we have no objective way. If you give me 2 spike sorting outputs, I cannot tell you which one is better than the other. And it's important to develop the methods on a wide range of regions. So here, benchmarking opportunities is really important. And with this, I would like to thank really the people that acquired the data. This is really the hard work at IBL. Right, to me, it's really the most intensive, and that was the hardest part. So those people are really a big part of everything we are able to do. And it seems like even spike sorting is easier than what those people have been doing. And of course, all of the IBL group, and I've highlighted the people that were instrumental in the spike sorting working group. And with this, I'll take any questions.
Questions for Olivier? Ramon? So in the pipeline that you show almost at the end, where you describe what is the bottleneck of every step, in pre-processing, you describe that is mainly IO bound. And am I right that this is because you cannot feed all the data into memory and you need to go over chunks, right? And I think that in a library, that makes a lot of sense, that you cannot assume that you have a lot of RAM resources. But in a pipeline like the ones that you have, what is the economics of use having enough RAM to avoid that problem? Is that something that you consider to like get rid of the IO problem over there?
For this, I'm not sure. Even with a lot of RAM, my experience is that if you try to load something like 200 gigs of RAM, you start getting very slow memory access. If so, because your array, your 2D array is flat in memory.
Right.
You start to doing a transverse slicing of your chunk. You're jumping a lot in memory, and you lose a lot of time. So what we do here, we split in chunks. Okay. So we are processing batches of 2 seconds, usually a power of 2 number of samples. And then you can tweak the memory setting by setting the number of jobs you want to run. The problem is that here we're limited by the CPU size.
Interesting. Thank you.
But yeah, that's a good point. Right now, our pre-processing does not maximize the RAM use, the memory use. It maximizes the CPU use. And maybe we should increase the batch size so that to maximize the memory use. It's a good point. We should try. But yeah, for LFP, we have people that have tried to load in 200 gigs in memory, and it doesn't scale. No, it doesn't scale. Probably get caching problems. Yeah, so I think you'd be better off to do what we've always been doing in signal processing. It's always to batch.
Yeah. And so in the rerun, you basically double the number of good units, kind of, in a sense. You change a lot of stuff. Any hints about, is there one that was the key to double this number? Is it the motion correction, the widening, pre-processing stuff? Yeah, any idea about what steps were crucial in maximizing this number of good units?
Yeah, I think it's clearly to me, it's the threshold. That's the main driver of the yield. But what really was useful as well is the whitening pre-processing, the whitening stabilization. And this allowed more units per recording. This allowed to have more recordings.
So I'm wondering how you handle units that pass all of your quality control metrics, but say are only present for like a quarter or a tenth of the session. Do you just count those as good units? And yeah, and in the analysis, how do you handle the units that are present for some trials but not others?
Yeah, we had the discussion with some PIs about this, and we say here there is no way to say that it's not task related. So they could be very well, especially since we have several protocols in some. We have a passive part of the. Maybe there's a neuron that turns on only for this passive part.
Okay.
So I guess I'm curious about how you think testing framework like math, those are originally doing math, like no testing, no CI. There's 5 kills from these CI, and how can we be testing to try to find these bugs out and looking at your data and being like, oh, this smells funny, you know, how can we test to try to find?
But the spike holes is coming from the signal processing is this should not have happened because you have a window manager and this should be unit tested. It's really hard after to write unit tests of a program that is already out there. So what we do at IBL, what I do is that I have integration tests on 13 canonical insertions throughout the brain. And if I do a major revision that I ship on the server, I'm going to run the spike sorting on all of those 13 insertions. And we have comparisons metrics for them. So right now, that's what I do before I ship a version, because I need to see on all of those regions how it behaves. So right now, it's your answer. It's one big integration test.
So basically you compare with previous kilosort runs.
Yeah, and I
Okay.
keep all of them, history of all of them, because if 2 years down the road that already happened, that someone says, hey, by the way, what did happen on version 1.5.6? Well, at least you can go back. So versioning, so a good code hygiene is versioning, tagging your commits, versioning. And this, there is no getting away for it. There will be bugs in the programs, and we just need to make sure we have a good versioning in all of our modules. That's a good takeaway for Pierre. When you were mentioning this, I was thinking, yeah, there's going to be bugs. You want versions on those things and make sure that you can go back.
On each component, we need versions.
Well, one last thing about the CI is that the CI, we run it, at least we run it on the cloud on GitHub, and it cannot be very expensive. So we have to make a quick CI on the unit tests. And we have a CI, internal CI on integration tests.
Okay, let's thank Olivier again. Unless there are other questions. So the next speaker is